So this presentation is going to look at how our project leveraged BIM360 to drive project performance on the project here in South Korea. So the way we were set up was from a very data-centric platformed approach. We had all relationships in data cross-referenced, linked back to the plans and actual status. A key component of how we drove execution was through something we call opportunity and constraint analysis, which is all about opening up the work fronts for the next group. We had a full construction BIM model that enabled visualization of all statuses, subsystems, all multidiscipline. And then we applied the process of progressive inspection. So this is where BIM360 came into play, and then very close collaboration with the contractor. So the scope we focused on was E&I, and the ability to get line of sight on cable tray installation to drive the whole E&I process. So the complexity of the project, and particularly the model file, was about 700 megabytes. So we had to break this down into much smaller chunks to make the functionality and the iPad hardware work for us. The discussions with the Autodesk team, BIM360 had never been applied on a project of this size in oil and gas with any success, and also it had never been applied to E&I scope. So we focused on, there were 9 main E&I rooms. We had 85,000 meters of cable tray, 1.1 million meters of cable. There was 18,000 panels or devices, which needed 45,000 terminations, 26,000 check sheets, and 9,000 instrument loops. And then we also applied this to 55 leak tests. So we want to have a look at the process. So our engineering model was developed in AVEVA, which meant we had to have a robust conversion strategy to link into Navisworks. Before we apply anything into Navisworks or BIM360, this is the setup of our construction database. So we pull all the engineering data, all planning data, all our construction completions data, all the contractor data into our construction management system to create the ability to plan, execute, measure, and improve. So it's all these relationships in the data that enable us turning the engineering model into a powerful tool for construction. So from the AVEVA plant, we convert into RVM files, which we then load into Navisworks. So there's a push-pull relationship between the database and Navisworks. One, we want to export equipment tags from the model to cross-check that we've got everything accounted for. And second, we want to embed further data into Navisworks, which then enables the BIM360 process. From here, we apply the Navisworks model into BIM360 Glue, which is the cloud sharing environment, and then be able to populate the field database with all the relevant tags and status that we want to capture. This then drives the field tablets where we're continuously uploading the latest model and pulling down the status that the guys in the field are capturing. So this is the process that is fully embedded in the Autodesk product suite. So then what we're doing is, again, it's a push-pull. We're pushing in priorities that we want our field guys to go and check, and we're pulling the real-time status back into our system for analysis. So all of this data was continuously analyzed on a daily basis with the provision of identifying really what cables could be pulled and where was our termination availability. So the outputs of this, we have a fully updated status model and all the data that comes with it. And what we do with this is we apply opportunity and constraint analysis. We drive to open work fronts. We have accurate field status, and ultimately it's communication of full model visibility. So the problem that we had, the project was about 70% complete. The contractor didn't report against individual branch IDs, only a linear meterage. So we had no visibility on actually which tray was installed. At the point in time the contractor was reporting, we were 65% of tray had been installed, but we hadn't started to pull cable. So the question was why? So what we needed to do was validate the status of tray installation. So we put in a process around progressive inspection to validate this. In parallel to this, we needed to understand what cable pulling figures could be achieved. And through our workshops with the contractor, their norm for a project of the size and scale of Hebron was 22,000 meters per week. An absolute stretch, they thought they could achieve 36,000 meters, but this wouldn't be consistent. And in order for us to sail away when we needed to, we knew our project need was in excess of 50,000 meters a week. So how are we going to go about achieving this? When we look at the process for E&I, The major equipment inside of rooms we had a very good handle on. That's why it's highlighted here in green. What we didn't have visibility on was the supports and tray infrastructure, which ultimately is what cables sit in, and that was what was holding up cable pull. We would then also need to know the status of the 18,000 devices, which would open up our termination sequence, which in turn then drives our static checks for commissioning. So what we needed to do was first get line of sight. Once we had line of sight, we needed to identify cable pull opportunities on a daily basis, and then we needed collective action, and this was then a repeated process. So what did we do? Initially, there was a manual progressive inspection process put in place. So the guys used nodal drawings, which is the cable routing layout drawings. One of the problems with this is not every single cable tray has a nodal reference. We were only ever going to get to about 85% of tray validation. Secondly, with just using drawings, it was actually difficult to locate scope in the field on a platform of this size. You can then see that there was very cumbersome recording and marking up using multiple coloured highlighters for the various punch status. I then had to return back to the office and do a manual takeoff of this and update a spreadsheet before I could actually get my hands on it to do the analysis to identify what cables could be pulled. So over a period of 55 days, we had 10 inspectors, and we validated a total amount of 4,738 meters of fully installed tray that we could pull cable through. And this was a very, very bad pitch for the project. Secondly, there was a time lag in the availability of this data, which was anywhere between 3 and 5 days. So about 30 days into this process, it was clear that we were never going to catch up and get line of sight. I'd already been coordinating with the guys at Autodesk, and we believed that we could put the BIM360 process in place and make it work for us. So that's what we did. So the difference is with BIM360, now we had a digitized process. So instead of having to continuously look for the latest revision of the nodal drawings, we could upload the latest model on a daily basis, which saves the guys a lot of time. Secondly, it was much easier to navigate and find the relevant part of the plant and then the tray that they were looking for. There was then continuation. You didn't have to flick through multiple drawings to find the next section of tray. It was fully continuous. It provided a very convenient method of recording, and we could upload the status instantly. Now, the benefits of this were very, very quick and apparent. In just 11 days, we had validated 5,957 meters of cable tray, which was 25% more in a fifth of the time compared to the manual process. This equated to a 630% efficiency in capture within the field, and also the data availability increased between 300% and 500%. So within a further week of this validation process, what we realized was our actual true status installation was 15% versus 75%. So what did we then do? So in order for us to achieve the record cable pull that we needed, what we first started doing was identifying the low-hanging fruit. So based on the granular nature of our punch categories we had applied into BIM360, we were able to identify things that were easy to complete. So this graphic here represents all the tray that just needed bolts adding. So this was things like our low-hanging fruit. Secondly, from our BIM model, what we had done is modeled all the tray and how many cable quantities ran through them. So we were able to start identifying exactly what tray we wanted the contractor to focus on, which would open up the availability of cable pull as quickly as possible. And finally, very, very close collaboration and hands-on work with the contractor from our construction team. So what we were able to quickly do was start a process where we were installing 3,500 meters of the right tray every single week. When we had accurate status of tray, we were able to identify available cable pull on a daily basis and group these cables to help the contractor be more productive. Our 14-week average was 54,000 meters of cable pull, which is absolute record norms for this yard, probably double what they're used to seeing. And our best week was 73,900 meters of tray. This was a fantastic outcome, considering many people didn't believe that this would work and it was a first of its kind. So after the early part of tray validation was such a success, we looked at seeing how we could apply this to the next phase, which was end devices. So when we look at the end devices, we said we had 18,000 end devices. The difference with end devices was the contractor actually reported which ones they had installed. So in the graphic you can see here, these were the red ones. So this made it quicker and easier for our inspectors to go out and check the ones that the contractor had said they had installed. The way we'd configured it wasn't just to look at is the device installed. We were able to see if the contractor had said it was installed, how many cables should be going to the device, how many the contractor had said were at the device. We could then validate them from how many cables had been pulled, how many were glanded, how many were terminated. So it was a much more granular level of detail, and this is through our BIM model that enabled us to capture this. What this then in turn created was our availability of terminations, and not just singular terminations, but where we could get into a panel and terminate many cables in one instance. This is much more effective and efficient for the contractor, but also too helps us preserve the equipment from opening and closing it multiple times. So the termination availability and the productivity we realized there then enabled us to identify loops which we could complete early. So in this example, the ITSS cabinets have been signed off. We could then check the power cables were signed off, the junction boxes, the instrument cables, and the devices. So through our data-centric approach, we can then use this information from BIM360 to identify which loops were available early. What we were able to achieve was 4,500 of our 9,000 loops were completed pre-MC. This is kind of unheard of numbers for the industry. We then use this to close out the final stage, which is cause and effects. This is the dynamic commissioning aspect. And again, we were able to get after this scope much quicker. So what we had done, we had taken the whole E&I scope, cradle to grave, based on the information we could capture from BIM360. We got line of sight on tray, which enabled us to identify which cables could be pulled. We supported the contractor by grouping these cables together to be more productive. We used BIM360 to identify which devices were installed, but also to capture exactly what the cable status was, which in many cases was further progressed on what the contractor was reporting. The termination efficiency was there, which then in turn drove the ability for us to complete loops far sooner and get into our dynamic commissioning of cause and effects. So the success of the E&I campaign was then taken into our leak testing campaign, which was then on the critical path. So we configured BIM360 to identify the 4 leak packs, and as you can see here, this is just one leak pack, highly complex, that covered multiple deck levels. So what we did, we coloured in all the valves as red, all the flange points as green. So this identifies what all the potential leaks are. So what this did, it improved visibility, but it also enabled us to be more efficient in our preparation for test. The way we configured it was that the guys in the field would then update each of the flanges and valves that they had been taped and tagged and they'd been isolated. So this ensured that we were best prepared from a safety perspective to engage in the test. So the benefits summary. So from a field data capture point of view, we had efficiencies of up to 630% versus a manual process. Inspectors were able to spend more time in the field versus printing the nodal drawings, checking for the latest revision, doing a manual offtake. Data availability increased from 500% versus a manual process and up to 600% based on the contractor's reported weekly status of devices. We had a much more granular level of accuracy, 15% of tray versus 70% what the contractor reported. Our productivity improvements in excess of 150% versus their norm, and our peak week was 350% above the norm of the yard. From an end device point of view, we were able to validate much more granular level of detail, which then in turn drove the terminations, which drove us to be far more productive and capitalize on loops far earlier in the cycle. And our leak test proved to be 200% more efficient in pack walkdown and preparation for test. So the benefits to the project. We created accurate project visibility. We identified and visualized opportunities and constraints, which enabled open communication, both internally with our management to our supervision and also with the contractor. We empowered our team to drive desired outcomes, and what we've done, we've realized a project sail away that ensures our first oil target of 2017 is achievable. Overall, we have a schedule reduction of 3 months over a 12-month period against our stewardship plan or forecast. And in turn, this 3-month saving alone is around $50 million worth of cost saving in PMT costs.